Welcome to another episode of Mr. Avila Physics. Today we're going to be talking about conservation of energy. Now, as we know, the total energy of an object consists of the sum of its potential and kinetic energy. Let's say, for example, that an object of mass m is lifted to a height h. The work done to lift that object would be equal to force times distance, which would be equal to mg times h, because the force needed to lift that object would be its weight, and the distance that we lifted it was h. So if we're taking this object right here and we're lifting it to this height h, then the necessary force would be equal to its weight, right? And the distance that the object is moved is h. So the work done is equal to mgh, which is also the potential energy of the object. So at this point, when the object is here, the total energy is equal to potential energy. But let's say that we drop the object. So the object was here at a height h, right? And we drop the object. So the instant the object is dropped, the total energy is still potential. But as soon as gravity starts doing work, right, then the work done by gravity is going to take the block, it's going to take the mass, and it's going to bring it down, and it's going to bring it down to the floor. Now, as the gravity starts doing work, gravity increases the kinetic energy of the object, as we know from the work energy theorem. And as the object falls, the potential energy decreases. So what we're seeing is that the work done by gravity in bringing the object down a distance h or d is equal to the change in kinetic energy, but it's also equal to the change in potential energy, because work is equal to the change in energy. So as the block got lower, the potential energy decreased, but at the same time, its kinetic energy increased. So as we can see here, at this point, the total energy is potential. As it falls, it loses potential energy because it's lower to the ground, but it's gaining kinetic energy because it's going faster. So at this point, half the energy is potential and half the energy is kinetic. And when it finally reaches the ground, the potential energy is zero because height is zero, and the velocity is maximum, so the total energy becomes kinetic. Now, how can we express this in formula form? Well, as we saw from the previous diagram, as the object gained kinetic energy, it lost potential energy. So that would mean that the gain in kinetic energy, the change in kinetic energy, is equal to the negative of the change of potential energy. All right? Now, if we put this on a formula, then we would see that the change in kinetic energy plus the change in potential energy would equal to zero. Now, how do we find kinetic energy or change in kinetic energy? Final kinetic energy minus initial kinetic energy plus final potential energy minus initial potential energy would be equal to zero. Now, at the beginning, let's keep going with this formula because this is a good expansion here. So then we would see that 1/2 m bf squared minus 1/2 m bi squared plus mghf minus mghi is equal to 0. Move the final values to one side, move the initial values to one side. we end up with a formula that says 1/2 mvf squared plus mghf is equal to 1/2 mvi squared plus mghi. And then this right here, this is the kinetic energy plus the potential energy at the endpoint. So this becomes the total energy of the object at the endpoint equals, and this is the sum of the kinetic plus potential energy, which is also the total energy. So what is this telling us? This is telling us that the total energy that an object had at the beginning or at any point is equal to the total energy that the object will have at any other point. This tells us that the total energy of an object is always constant. Okay, so this is very important, right? This tells us that throughout the path of the object, the total energy is constant, which brings us to the law of conservation of energy, which the law of conservation of energy states that the total energy of an object is neither increased nor decreased. Energy can only be transformed from one form to another or transferred from one object to another, but the total amount of energy is always constant. So let's try this example. Pause the video here, take a couple of minutes, and see if you can solve this example. All right, welcome back. So let's see here if we can solve this example right here. So it says, assuming the height of the hill is 40, so this is equal to 40, right? And the roller coaster cart starts from rest. So right here, the initial velocity is 0. Calculate the speed of the roller coaster at the bottom. So velocity here. And calculate the height at which the velocity would be half. So calculate h here where the velocity will be half. All right, let's start with A. So I know that from the conservation of energy, I know that the total energy at point 1 is equal to the total energy at point 2, or initial and final. Now, the first thing I have to do is I have to choose a point 1 and a point 2. So I'm going to choose this point as point 1, and I'm going to choose this point at point 2. So kinetic energy at point 1 plus potential energy at point 1 is going to be equal to kinetic energy at point 2 plus potential energy at point 2. Since I know that the initial velocity is 0, then the initial kinetic energy is 0. And I also know that the final height is 0, so that means that the final potential energy is 0. This tells me that mgh1 is going to be equal to 1/2 mvf squared. Cancel mass. This tells me that the velocity at the bottom is going to be equal to the square root of 2gh, which tells me that the velocity is going to be equal to the square root of 2 times 9.8 times 40, and that is 28 meters per second. All right, so now let's try with B. So at B, they're asking us to find this point. So I'm going to go ahead and say that this is going to be point 3. So that would make the total energy at point 1 equal to the total energy at point 3. So I already realized that at point 1, my entire energy is potential. But at point 3, I have both potential and kinetic. Why? Because I know that it is at a certain height and it is moving. So mgh1 is going to be equal to 1/2 mv3 squared plus mgh3. So cancel the masses, and then I will have 9.8 times 40 is equal to 1/2 times v3, which is 14, right? Because we want the velocity to be half, plus 9.8 times h3. And from here, we can solve for velocity. So 9.8 times 40 minus 0.5 times 14 squared divided by 9.8. That gives me a height of 30. So h3 will be equal to 30. So 30 meters from the lowest point, the velocity would be half of its maximum velocity. All right. And here is the solution from your textbook. As we can see, we have the same values, right? 28 and 30. All right. Let's try this next example right here. A ball of mass 2.6 starting from rest. So the velocity here is 0. Falls a vertical distance of 55 centimeters or 0.55 meters before vertically collided with a spring which compresses an amount of 15 centimeters. Okay, sorry. Determine the spring constant. Okay, so here, same thing, right? I know that total energy 1 is going to be equal to total energy 2. So I'm going to look at this point as point 1, and I'm going to look at this point as point 2, which means that, okay, the total energy at point 1, potential plus kinetic plus elastic energy is equal to potential at 2 plus kinetic at 2 plus elastic energy at 2. Since at point 1 I know that it is not moving, kinetic energy is 0. And there's no springs here compressing or stretching with mass 1, so the elastic energy is 0. So at point 1, the entire energy is gravitational. At point 2, okay, the mass stops moving, so there is no kinetic energy. But is there gravitational potential energy? Well, that all depends on where do we take a reference point. If we take a reference point here, at this line, then yes, there will be negative potential energy here at this point. If we take our reference point as being this line, then no, there will be no potential energy at this point, okay? So I'm gonna go the simpler way for me, and I will take my reference point to be here at the bottom. So then there will not be any gravitational potential energy, and I will only have elastic energy. So then M 2.6 times G 9.8 times height 0.55 plus 0.15 equals 1/2 K times 0.15 squared. And from here we can solve for K, and we get a value of K equal to 2.6 times 9.8 times 0.70, right, times 2 divided by 0.15 squared gives me a value of 1,585.4 newtons per meter. And this becomes value of K. All right, okay. So here's 1590, 1585. Okay, so here's one solution. Now there's another solution that we can do here, okay? Which is actually what we did. Okay, the way we solve the example is this solution too. This first solution breaks this into three sections, right? It breaks this into, let me change the color here. Change this into potential energy, whoa, wrong color. Change this from potential energy to kinetic energy, and then from kinetic energy to elastic energy. And it'd be the same thing. You would start with potential energy, and then you will calculate the velocity here, and then you would do kinetic energy to elastic energy, which is this solution right here. From here, they calculated the velocity when it reached the spring, and then from here, they went and kind of converted kinetic energy to elastic energy. Whichever method you want to do is fine with me, okay? Just remember to always show your work. All right, now we're going to talk a little bit about energy loss. The examples that we've seen and conservation of energy ignores all types of frictional forces, but we know that friction exists in the world. And how do we account for friction when we're dealing with energy loss? So, when there are external forces in a system, such as friction, then we still have the conservation of energy, but we need to account for those energy losses, right? So let's say, for example, the object that we covered before starts here at a height h from the ground, right? And it falls, but there's air resistance going upwards, okay? So air resistance, it's an external force, and this force does work on the object because it acts through a certain distance. And this work, the work done by frictional forces, is what we call the energy loss. So the system would still conserve its energy if we consider those losses as part of the equation. So our equation changes a little bit. We have the total energy that we had at the beginning minus whatever energy we lost along the way, and that's going to be equal to the energy that we are left with at the end, right? Now, in equation form, this looks a little bit different. So in equation form, this would look like this. So the total energy at point 1, we would have 1/2 mv squared at point 1 plus mgh1 plus 1/2 kx1 squared minus energy loss, which is the work due to friction, which is equal to friction force times distance, right? And this is going to be equal to the total energy that we have at the end, 1/2 mv2 squared plus mgh2 plus 1/2 kx2 squared. And this formula right here is the formula for the conservation of energy when we include energy losses. There we go. Okay. So in summary, when there's friction, friction does work and it causes an energy loss. It causes heat or warmth. Okay. All right. Let's look at an example. So the roller coaster car reaches a vertical height of only 25 feet on the second hill, where it slows to a momentarily stop. So here, the final velocity is 0. It traveled a total distance of 400 meters. Determine the thermal energy produced and estimate the average friction force on the car whose mass is 1,000 kilograms. So this thermal energy is heat, which is the work done by friction. Okay, so here we're assuming that it starts from 0 as well. Okay, this is 40 meters, and it reaches here. So since they're asking us to find thermal energy, that means that they're asking us to find friction, which means that there are going to be losses. So that means that the total energy at the beginning minus the energy loss is going to be equal to the total energy at the end. So at the beginning, there's no springs, so there's no elastic energy. The cart is not moving, so there's no kinetic energy. So that means that we have potential energy. So the potential energy at 1 minus the energy loss, right, which is the work done by friction, is equal to the total energy at the end. Here at point 2, there is no spring, so there's no elastic energy. The cart is not moving, so there's no kinetic energy, so there's only potential energy at the end. Which means that the work done by friction, which is the same thing as thermal energy, is going to be equal to the potential energy that we had at the beginning minus the potential energy that we had at the end. So this is going to be equal to mgh1 minus mgh2. This is going to be equal to 1,000 times 9.8 times 40 minus 25, 15. So the work done by friction is going to be equal to 147,000 joules. 147,000 joules or 147 kilojoules. All right, so this is the thermal energy or the work done by friction. Now we have to estimate the average friction force. So in order to do that, I'm going to go ahead and go and say, all right, so the work done by friction is going to be equal to friction force times distance. All right, so friction force is going to be equal to the work done by friction divided by the distance. This is going to be equal to 147,000 divided by the distance that friction acted upon. Now, careful. The displacement of the cart is just this straight line right here. But the cart did not travel through air, and friction is the force of contact between two surfaces. So then friction acted on the cart throughout all this distance right here. And this distance is 400 meters. So which is why I'm dividing it here. So that means that the work of friction is going to be equal to that divided by 400. The force of friction is 367.5 newtons. And now we can't really find the coefficient because normal force is not constant in this case. Normal force is changing all the time because the cart is changing its angle all the time. So we cannot find any more information about this. All right, okay. So here we can see, right, little steps to what to do. And here we go. This is the thermal energy, 147,000 joules, which is what we did. And friction force, 370. Okay. Just, yeah. All right. Hopefully this made a little bit of sense, and thank you for watching. I will see you next time.